There are two ways to gauge the strength of an acid or a base. One is by looking at the magnitude of the Ka or the Kb. That'll give me a picture of how far forward the reaction goes. Another option is to just calculate a percent dissociation. Now we said that strong acids and strong bases dissociate 100%. Weak acids and weak bases dissociate by a fraction. So we can actually calculate that percentage. An ice table is going to get the job done. Lactic acid is a waste product that accumulates in muscle tissue during exercise. I'm going to write an equation for this lactic acid, C3H5O3. If it's in solution, the only other particle present will be water. If lactic acid is an acid, then it's a hydrogen donor. So we'll lose this hydrogen, and we'll be left with the lactate ion, C3H5O3 minus, and hydronium, H3O plus. We're going to ice table this, and watch how easy it is. The original concentration is 0.1 molar. I'm not going to use the water in any of my final calculations. It's a pure liquid, so we'll scratch that out. And initially, the two ions are at 0. Now, instead of having to shift this forward by x, when they say that the acid is 3.7% dissociated, that tells me how far forward we go. I think we had one of these back in the last unit where maybe there was a reaction that went forward by 20%, or 20% of the original reactant is consumed at equilibrium. All we got to do is take 3.7% of my original concentration. So I got to flip the decimal, 1, 2. So I'll do like point decimal 0.37 times my molarity, 0.1. And bingo, this is going to give me x, 0.0037. That's kind of like our x value. I don't need to solve for x because I know the shift. Now, if we're going forward, this is going to go down by 0.0037, and my product ions will go up, 0.0037, and up by 0.0037. And one nice thing about acid-base ice tables is that you're usually dealing with 1-to-1 ratios. So now all I got to do is add and subtract. So I got 0.0963. I can put that in as molarity, moles per liter. And these guys will just be 0.0037 and 0.0037. Well, look at that. I love it. So now here they're asking me to calculate the value of Ka. Yeah, I could do that. In order to calculate the value of Ka, you got to be able to fill out the ice table, because we need to have all these values in the equilibrium line in order to calculate the equilibrium constant. So somehow they got to tell me or hint at x, how far forward am I shifting? That's what percent dissociation gives us. So now all I got to do is say products over reactants. I could put this in as squared if I wanted to, I suppose. Products over reactants, 0.0963. If this is a weak acid, it's only 3.7% dissociated. I'm expecting a small K value, maybe about 1.4 times 10 to the negative 4th. Yeah, I'm expecting a K value that'll be less than 1. So that seems legit, right? There it is, percent dissociation. It gives us X. How forward do I shift?